At the first virtual Ifac World Congress, all plenaries and semi-plenaries are accompanied by a live element. This presentation is followed by a live panel discussion, where experts in the field recapitulate and debate on related ideas, questions, and open problems.
I'm the director of the Robotics Institute, and I will talk to you about our work on the bipedal robot Cassie. So this is my students. All of the good things you see here are due to them. Any screw-ups are due to me. I take full responsibility. We thank NSF for supporting our work. So this is a Cassie bipedal robot. You will see here it's under operator control. There is no perception on the robot other than an IMU and encoders. There are no force sensors in the feet or anything like that. This is the wave field at the University of Michigan, right behind the aerospace building. It's been a dream of mine to do this, and one of the big painful parts of my life is watching children just run across this thing carefree, and my robots being a total disaster on it until 2 weeks ago. One of my students pulled off this. What I want you to see is some of the things that a robot is capable of doing when it's under operator control, and what we want to be able to do is accomplish this under autonomous operation, and I'll be talking about that next. But notice here he's approaching it somewhat cautiously. This is the first time through these big humps. We've been up and down the valleys with other robots before, but we've never had a robot able to clear these humps. It's a single gate. The robot is not changing gates as it moves. What the operator is doing is just controlling the speed that the robot is advancing, direction, but of course all of the real-time balance is being done by the robot. So we make it through the humps, and then we get to the very end. And one of the things that my lab is extremely well known for is we're brutally honest with where we are in the state of the art. And well, yes, face plants. That's our state of the art. So now this is our Cassie robot when we equip it with an autonomy package. So we have an RGBD camera, which D means depth, and a Lidar. And so this is also on the wave field, but navigating around it on the sidewalk. This was last summer. And what I want to do on the next few slides is just walk you through what's actually going on in terms of building this real-time map that a planner is able to use to develop waypoints that are then sent to the local controller that you saw just performing on the wave field. So what happens is when the camera image comes in, it is being segmented with a neural network, and then semantic labels applied. So what this means is the robot can reason about the scene because it knows what is a sidewalk, it knows what is grass, it knows what is people, it knows pixels that are assigned sky, building, and grass. The next thing we do is we become extremely proficient at fusing LiDAR and camera data. So what you see here is LiDAR data on the right overlaid on a camera image. And then when you really get this right, and then you take multiple LiDAR frames and fuse them together with an invariant extended Kalman filter, which is processing the IMU data, you get this beautiful map that you see on the lower right. And then that leads to us being able to build in real time the map that you see in the lower middle of the screen. Now that map looks like simultaneous localization and mapping is happening because it looks like a loop closure has been done, but after 120 meters of walking, the robot misses the final target point using dead reckoning by a mere 10 centimeters. That's 1 part in 1,000. Now to accomplish this takes an amazing amount of system integration, which is extremely hard, but my group has built that up. The next joy that we're going to have is when we can do this level of autonomy in much more loosely structured environments where we are heading to the forest. Right now, in terms of Jing Sun's theme, it's painful just thinking about how we're going to accomplish this. And now, Ilya, take it away.
Thank you very much, Jesse. So it's my pleasure to contribute to this discussion of exploring dynamics of integrated systems by making a few remarks about flexible aircraft. And one of the recent trends in commercial aviation has been towards airplanes with high aspect ratio wings, basically longer wings. Such wings reduce fuel consumption, but they are also more flexible and can experience high deflections and loads as they're exposed to maneuvers and gas disturbances. So for such a flexible aircraft, it is more challenging to ensure that critical loads do not exceed specified limits, which are imposed to guarantee aircraft safety and structural integrity. At the more extreme end of flexible aircraft are very flexible aircraft, or VFA. They include high-altitude, long-endurance platforms, such as Aurora Odysseus and Airbus Zephyr. These vehicles are solar-powered and can stay up in the air for days to provide observation and communication relay services. As you can tell from these pictures, these aircraft rely on high aspect ratio wings, high lift-to-drag ratio, low structural weight, multiple propulsors, and multiple aerodynamic control surfaces for their mission. So these flexible aircraft are quite challenging to control due to reduced separation between rigid body and flexible modes and possibility of large deformations in nonlinear behavior. Typical physics-based models for such vehicles are high order, between 100 and 1,000 states, and it is not straightforward to directly use them for control. There are multiple control effectors, which can, in extreme wing deflection cases, even change their role. For example, an aileron can start acting as a rudder. There are also numerous structural and control effector constraints which need to be enforced during aircraft maneuvers or when responding to gust disturbances. Some of these challenges are exemplified in an aircraft called Exhale, which was built by my colleague at the University of Michigan, Professor Carlos Cesnik. If you attempt to pilot such an aircraft remotely, that is largely open loop, you very quickly come to understand the challenges or pain in dealing with its dynamics. This video illustrates some of the early flight tests and shows some of interesting dynamics of this aircraft, as hopefully you can see from this video. And ultimately, an attempt to control this dynamics is unsuccessful, ending in a crash landing that we will hopefully see here on the video shortly. So you can have a lot of fun trying to control such an aircraft. Of course, the results can be improved with some level of control on board, and this video shows a more controlled flight and successful landing of such an aircraft. Carlos and I have been collaborating on trajectory following, maneuver load elevation, and gust load elevation problems for such and similar aircraft. In fact, in our current work with Carlos, our PhD student Matias Pereira, and Dr. Fabio Vetrano from Airbus, we've been developing maneuver load elevation system for flexible aircraft, which we call MLA Governor. This MLA Governor is based on model predictive control, and its advantage is it can respond to predicted load constraint violations at multiple points on the aircraft, rather than react to already occurred threshold violations as existing MLA schemes do. The way MLA governor alleviates loads is by modifying reference commands, such as the flight path angle that you feed to the nominal flight controller, and by directly modifying operation of the control surfaces dedicated to MLA, such as outer ailerons. And with this, it's my pleasure to invite Professor Kira Barton to continue the discussion.
Okay. Ready about this? Of course, I'm sorry, I can't actually find my file at the moment. But what I would like to talk to you a little bit about today, very briefly, is the area of manufacturing. And in my group, what we focus on is really modeling and control in manufacturing and robotics. And particularly, we've been looking into the ideas of smart manufacturing and how to think about using a variety of different technologies and capabilities so that we can try to improve performance and think about being more agile and responsive. And this is particularly true as we can see examples in the most recent several months where the ability to respond and adapt to changes and modifications is extremely important. Now with manufacturing, manufacturing is naturally a very hierarchical system. And so we have dynamics and interactions and really decisions that have to be made at every level. And so one of the big challenges that we see is how do we effectively sort of transfer information and understand the interactions across these different levels. We look at this as a system level type of problem or challenge really, where what we want to do is to be able to effectively take decisions and information and knowledge, and we want to integrate it across the different levels. And when we start to do that, we have lots of different system integration, things that we need to think about, and we have interactions that we need to consider from multiple different planes. So let's consider from the process standpoint, there are interesting dynamics that we can share just really from a process side. So if you look at an example like additive manufacturing, this is a really nice emergent area that has lots of different dynamics that come into play, particularly when you start to look at the interactions that you have between the surfaces perhaps that you're printing onto and the interactions of that material base with the new materials that you're putting down. Now you couple something like that with the other aspects of what's happening at the process level, and you can start to see other kinds of interactions. For example, in the robotics side, so perhaps the material handling. Now, classically, you would see pick and place type of more static interactions where you can start to learn these behaviors and have a very controlled environment. But what we're starting to see is this transition away from that very static, very sort of predetermined set of conditions towards a much more interactive and flexible system where you now want to look at the interactions between a robot and a human, and you want to have these collaborations going on throughout the entire system. And so now that's just two examples at the process level, but what's really interesting is that what we know from a system perspective is that throughout the whole enterprise, really, you have behaviors and interactions that come into play. And so things that happen upstream are going to have an impact downstream. And so being able to model these interactions and understand the impact of them, and then start to do things like predict when you're going to see anomalous behavior or how that behavior might sort of propagate through the system. That becomes a really interesting opportunity to start thinking about these interactions and how to model them. And of course, ultimately what you want to be able to do is to make decisions. Much like we saw in Professor Sun's talk, these are variable time scales. Depending on what your objective is, you need to be able to do things in microseconds to milliseconds to seconds to even hours. And so you have all this variability and these interactions. And of course, a good example that we've seen, as I mentioned in the last couple of months, is how do we make this more flexible and agile so that we can respond to fairly significant changes that might be going on and yet be able to do it in an agile and effective way. And with that, I'd like to thank you and go ahead and pass this on to Wei Peng.
Okay. Thank you. So first, I would like to thank Professor Jin-san for the invitation for the panel for emerging dynamics of integrated systems. So many of our control guys work on your favorite optimal control optimization problems. These are just equations you don't need to pay much attention to, but this is from a hybrid vehicle research I work on with Professor Jesse Grizzle many years ago. And mostly for the so-called pain and joy, I would say most of the time it's joy. We really learn something new when you make two changes to your favorite optimization problem. One is if you look at a larger state space, or you relax your constraint. So many of the times we look at the equality constraint and inequality constraint as if there's nothing you can do with those. But in many real applications, you actually can relax the constraints. So I'll give you two examples of when you enlarge your scope, you look at different problems, the findings are totally different. So the first example I gave is an eco-routing problem. Eco-routing is opposed to fastest or shortest routing, which your typical Google map and so forth will give you. And we really want to find what about eco-routing, meaning you want to minimize energy consumption. So what we did over the last few years is first we collect data from many trips, and then we build an energy consumption model for the city of Ann Arbor. And then we actually solve the eco-routing problem. This is a real-time. This actually, we can calculate everything very, very quickly. We divide the city into many origin destinations. And by clicking the origin and destination, it will solve all the eco-routing, fastest routing, and so forth problems. So all good. And the major finding from the solution is that we found when compared to fastest routing, usually you are able to, on average, you can save about 13% energy if the trip is long enough. Longer trip, you save more. But in comparison to the fastest routing, you also pay a price in terms of more time. Everything here is done by a traffic simulation software, not by a simple MATLAB simulating type of computation. So this is a typical eco-routing solution, and obviously nothing here is surprising. However, when we enlarge our scope, and basically we say going forward, there will be connected and automated vehicles coming. What if you share your intent for routing choice, not your position velocity necessarily, just telling a central location what is your intent for routing, then you go ahead and solve the problem again. It turns out that you are able to save both fuel and time. And the main reason here is in urban congested areas, the capacity is very limited. And if there are some cooperation, you are able to avoid congestion, which is the main reason you can save both fuel and time. Another problem about relaxing constraint is a pause and glide example. We all know that modern vehicles have many horsepowers, and when you are coasting on the highway, typically you are only using a small number of the horses you have. So this enables a phenomenon called pause and glide. As you can see, we use the concaveness of the powertrain generation, and we are able to oscillate between the idling point I and the tangent point T. And if you oscillate between these 2 points, your average fuel consumption is lower than that of point C, which means you are saving fuel. So the concept was basically resulting in more or less you are following the vehicle in front of you, but you are relaxing the constraint. You don't need to follow it precisely. If you pause and glide a little bit, you can save a lot of fuel. More recently, some Hitachi researchers pick up our idea and implement their testing in Japan, and they were able to find 8 to 38% fuel consumption reduction. So in conclusion, again, it's mostly joy. If you enlarge your scope or you relax your constraints, you can find very surprising results. And that's really very fun that my group has been doing over the last few years. Thank you very much. Jing, you are on mute.
Well, thank you all for the panelists for the very interesting discussion. And I was hoping that I take all the joy and leave the pain for my colleague to deal with. But as you can see, they are all accomplished researchers, and I see them as super integrators, not just numerical integrator. As you can see, they show different flavor of system integration and system dynamic aspect. So we have about a few minutes left. I would like to through just one last question to the panelists, including the chair of the session. What do you see as the biggest challenge, or the pain, or the most rewarding part of integration and exploring the dynamics? So can I start with Professor Asama?
Yeah, thank you very much. And I'd like to thank you a very impressive and excellent talk. It was very, inspiring. And I actually saw emerging is a very, complicated function. So maybe it is a kind of joy. It's a very good challenge. But in other aspect, we should, guarantee some kind of safetiness when you use the technology in real, physical world. So that is very another challenge we should do. Thank you very much for your arrangement of this panel discussions.
Well, thank you. Kira, you have anything else to add?
Sure. So I would say that one of, I think, my favorite parts of particularly the integration at the manufacturing side is all the different dynamics and the disciplines that come together to try to create a solution. And so you get to work with folks from a variety of different backgrounds, all looking at trying to solve different kinds of problems. And I think the challenge with bringing everyone together and getting to, similar vocabularies and a group objective, and then everybody brings their expertise and skills, is one of the main joys of getting to work at that system level.
Thank you. Jesse?
I'll be very down to earth. In the robotics area, of course, we're pretty heavily tied to CS. So there's a huge struggle with how much you do with neural nets and how much you do with analytical methods. In the videos I showed you, the only neural net was used on the segmentation of the image. Everything else was an algorithm, and that gives us better modularity, but it's still a big fight in the field.
Thank you. Ilya?
Yeah, so for what I presented, first I should say that I'm very fortunate to be part of Airbus University of Michigan for air servo elasticity, a very flexible aircraft. The joy part is that it gave me an opportunity to work closely with colleagues from other disciplines, including structural mechanics, multidisciplinary design optimization and also flight physics at Airbus. And of course, the pain or the challenging part is that, well, there's different kind of control challenges we have to deal with, in particular dealing with high-order models and complicated dynamics, as well as issues that go beyond control and integration of design aspects of aircraft and control aspects.
Well, will you have the last word?
Yeah, okay. So I think the biggest challenge is to keep learning the knowledge that you need for that particular domain, that application. Of course, if the future is all about data science or neural network, you don't need to have any knowledge of the application. But usually I think most people at the University of Michigan that work on real applications happen to believe that physics knowledge, math knowledge is very important to understand the plan instead of just relying on big data and computer to do learning for you.
Thank you. Well, thank you all. And I think we have reached consensus. Seems like there are a lot of challenges and opportunities, exciting and abundant. And pain is not the word to describe it. And again, I want to thank all of you for participating in this live panel, and special thanks to all the panelists for your enlightening comment and share the insight. Thank you.
Thank you very much.
Thank you.
Thank you, Jean.
Thank you. Bye-bye.